Hello everyone, welcome to the channel. Today's topic is AM simulation using Matlab. Dear friends, here we are going to simulate amplitude modulation concept for a different modulation indices. Similarly, we could be able to find what are the time domain waveforms for the different modulation index. And finally, we are able to see frequency domain waveform for different modulation index. Before we start simulating amplitude modulation concept in Matlab, we will observe what are the steps involved in simulation. First, we will accept the message amplitude and frequency by using input command of Matlab, and then we will generate a message signal. The same is plotted in the figure window. After that, we accept the carrier amplitude and frequency. We will generate the carrier signal and we are going to plot the carrier signal over the figure. Later on, we will determine the AM modulated signal from standard formula. Okay, that standard formula goes to EC plus M of t multiplied by cos 2 pi FCT. Okay, fine. So later on, we will be plotting the same modulated signal. Then we will compute FFT of the modulated signal. In the sense, we are converting a time domain signal into frequency domain signal, and then we are going to plot the frequency response of the modulated signal. Let us see how can we simulate the same all the steps by using Matlab. So I'll be opening the Matlab environment for the same. So you can observe here. So this is our editor window. Okay. So the code is already written here. So I'll be explaining stepwise what are all the things we are doing in the simulation. Fine. So let us observe these three instructions. Like these are all the very fundamental instructions we people use to write while writing the any type of Matlab code, which will help us in clearing the command window, workspace, and the inbuilt functions which are running in back. Okay, let us see. CLC will clear the command window. Similarly, clear all will clear the workspace and command window both. And coming to close all, the hidden functions which are already running, they are all closing. And after this, our programming, our Matlab environment will be ready for new simulation. Fine. Let us observe what will be our first step. First step is to accept the message, right? Message signal amplitude and frequency. You can observe here EM message signal amplitude, FM message signal frequency. So by using input command, we are accepting the message amplitude. See, input message signal amplitude will be inputting here. Okay. Similarly, we will be taking the message signal frequency, and these two things are available in EM and FM here. Okay. So after that, for the carrier signal also we need carrier amplitude, so that we are taking from this input input instruction. So it will be stored in a EC. Similarly, this is a input statement we are using for getting the carrier frequency. Okay, this is carrier frequency, this is carrier amplitude. After having this message signal amplitude and frequency, carrier signal amplitude and frequency, we have to define time. So question arises, what for time definition is required? Because in order to plot our signal, in order to plot our message signal or a carrier signal, time axis to be there, because based on the time as an independent variable, we could be able to find what are all the value for C of t, M of t, like. So that's what we are defining here. T is equal to 0 is to 0.001 is to 1, means moving from 0 to 1 we are getting 1000. 0.001 implies we are getting 1000 points of time. Okay, so that's a thing, that is the definition of capital T small t here. So which indicates there are 1000 points while moving from 0 to 1. Later on, let us observe here M of t is equal to, M of t means mt is equal to m of t, message signal, okay, which is given by message amplitude, okay. Dot star is an array multiplication, okay, cos 2 pi fm into t, okay, message frequency into small t, which we have defined here, okay. Later on we are taking a subplot having four rows, okay. So first subplot figure will be plotted for message signal. You can observe here, plot t comma m of t, okay. So the first message signal will be plotted in a subplot 1, okay. You can observe here, plot t comma m of t, okay. Here line width we have considered because to make that waveform should be easily observed, okay. So for that line width is mentioned. If you don't wish to go for this, so you can close it here only. This plot you can close it here only. For better visualization, this line width is taken, fine. After that, no doubt there is a x label indicating x is a time, okay, and y label indicating y is an amplitude, fine. Then title showing saying that this is a message signal, fine, or sine waveform. Now coming to, so if we want, like, we can write message signal also, okay. So I wish to go for the same because it will be easy for us. Message signal, fine, okay. So after this we are going for plotting the carrier signal, okay. So let us observe ct is equal to ec cos 2 pi fc into t, okay. So plot 2 will handle the carrier signal. Let us observe 4 1 2, in the sense among the four rows, in the second row we are having carrier signal, okay. And we are plotting carrier signal with t comma ct, and the line width is for your means of, in order to increase the line of the waveform, okay. If anyone is not interested, they can close your bracket here for the plot. Then what we will be going for, once again, x label, y label, and x label here once again it is a time, y label here it is amplitude for the carrier, and title is for carrier signal, okay. Title is for carrier signal, you can see here, okay. So apart from this, what we have to see, we have to plot, we have to even plot modulated signal, okay. So for the modulated signal, what we have to do, we have to apply the formula for the amplitude modulation. So this is the formula for amplitude modulation. Let us observe what is the formula. EC, amplitude of the carrier signal over which a message is varying, right? So that's what MT, EC plus MT, in the bracket I am taking dot star. Why this dot star is, it is an array multiplication, okay, cos 2 pi fct, okay. Here you can observe that, like, in case of a AM modulation, carrier remains constant, amplitude is going to change, right? Carrier remains constant, amplitude is going to change as per the changes in the message signal. So that's what the definition of AM. So we are fulfilling that AM definition with this formula, and we are storing the variable in a S of t or st. And the same plot is available in our subplot as a third row plot, fine. So and you can observe here what we people are plotting here, t comma st, we people are going to plot t comma st, and this is a line width as usual, okay. X label goes to time, y label goes to amplitude, and title goes to modulated signal, AM modulated signal, okay. Coming to now the last step, that is converting this modulated signal S of t, converting this modulated signal S of t into S of f. S of f is our, yes, what it should be, it should be a frequency domain contained for the S of t. So as a part of which S of f is equal to FFT of fast Fourier transform of S of t. Means what it will do, this FFT of S of t will convert S of t, whatever the time domain signal is there, that will convert it into frequency domain signal S of f, okay. In this frequency domain signal, no doubt we are having amplitude and also angle in consideration, because it's a plot, complex plot. It's a complex plot, S of f, which is a frequency domain plot, and it is of complex number plot. Fine. So you can observe, so where we are plotting that S of f is a frequency domain content, right? For the S of t, S of f is a frequency domain content for S of it. And we people are plotting that frequency domain content in fourth figure of that subplot. So let us observe. So what are we plotting? You have to take care here. This is very interesting. Otherwise, your plot will not be proper. Your plot will not be proper. You can observe here, plot real time of S of f. Here you are not considering that t comma s of t comma s of f. It's not there. It's directly that we are plotting real part of s of f, and the line width we are taken because in order to make that line is to be observable. Fine. And the title here goes to, it's a frequency domain. It's a frequency domain of AM signal. Okay, so frequency domain representation of or spectrum. You can say the spectrum also, no issue. Spectrum of, I will take spectrum of AM signal. Okay, so this is a spectrum of AM signal, and after that you can observe here. So one instruction is given, like while we started our simulation, at this time it is mentioned that AM simulation done for various modulation index. So in order to know what is modulation index, this instruction is written like modulation index is equal to EM, amplitude of message signal, divided by amplitude of carrier signal. Already we know that, like the concept of modulation index, for a better amplitude modulated signal, the modulation index should be less than 1, and we will have a different waveforms for different modulation index. Okay, we will observe that. I will simulate and let you know that. Okay, so for modulation index less than 1, what will be the waveform? For modulation index more than 1, what will be the waveform? For modulation index equal to 1, what will be the waveform? And even its respective frequency domain analysis also we can see. Okay, shall we move for running this code? So I would like to go for run, running this code with a breakpoint. Okay, so that it will be easy for us to digest well. Let us observe where and all I can put the breakpoint. Where and all I can put the breakpoint. It's I feel like after message signal plotting, after message signal plotting, I would like to give one breakpoint. Okay, and then after carrier signal, like that, all the four different signals I would like to take one breakpoint. I think it's okay. So up to here first breakpoint, and I'll move to the next. At this stage second breakpoint, so that once I run first code for up to first breakpoint, I could be able to see message signal. For the second breakpoint, I could be able to see carrier signal, and for the third breakpoint, I could be able to see modulated AM signal. And after that, yes, yes, no, fine. After that, we could be able to see modulation index and frequency spectrum. Fine, fine. I'll be running the code. Let us observe what is appearing in the command window. Yes, yes, it's asking for enter the amplitude message signal. Okay, enter the peak amplitude of the message signal, means it is asking for EM, message amplitude. So I would like to take 3. Fine. Next, enter the message signal frequency. I wish to go for 10. Okay, next, enter the peak amplitude of carrier. I would like to take 5. See, observe all of you, like if I take 3 as message input and 5 as carrier amplitude, then it goes for modulation index less than 1, because 3 by 5 goes to 0.6. Okay, and what about carrier frequency? Actually, in everyone mind, usually carrier frequency should be more than 1k 10k, like that, because my message frequency I taken like 10. Okay, because compared to this message frequency 10, I should use very high frequency of carrier signal. But in our simulation there is a limitation, like I have taken t is ranging from 0 to 1000. So within that I have to show the uh, within that 0 is to 0.001 is to 1. I have taken, no, from 0 to 1 I have taken 1000 iterations of time. So as a part of which in order to better get a better visualization, I am taking 100. Okay, in realistic value it should be more than 1000 or more than 5000, 10,000, like that, because carrier frequency is very very high compared to message frequency. If I go for running the code, what we will observe. Yes, yes, you can observe here. We have got message signal. Okay, we have got message signal of 3 amplitude. You can see here 0 to 3 minus 3. Fine. But many of you, we people may get confused that why only message is there. Is there any error in the command window? No, there will not be any error. But what happened, do you know what happened? Because of this breakpoint only our program is executed up to here. Now I will run the code once again. You can see I will continue the code because up to here message is plotted. You can observe here message is plotted, correct? Now I would like to go for rest of the code. See, I would like to go for this, right? So what we have to do, we have to continue the code, right? So that carrier signal will be observed. Fine. Let us observe. Okay, I'll go for the, just a second, I'll go for the figure. Yes, you can see here in the figure we can be able to get a carrier signal also. You can see carrier's amplitude is 5 to minus 5. Yes, carrier's amplitude is 5 to minus 5. That's also fine. Okay, after this you can observe our code moved from message signal, carrier signal. Now it is at modulated signal, right? So if I run this once again, I could be able to see modulated waveform. Let us observe that in a figure window. Yes, modulated waveform you can see here. Okay, this is under modulated waveform, under modulated AM waveform. Okay, let's see how the spectrum looks like. I'll be continuing this. So spectrum and the modulation index. You can observe here very interestingly. Modulation index we have got 0.6. We have got modulation index 0.6 because EM was 3 and EC was 5. 3 by 5 goes to 0.6. Okay, fine. But our area of interest is to get frequency spectrum of AM signal, right? Yes. We got it. We got frequency spectrum also. Let us observe. See, this is the frequency spectrum. Last 4 is to 1 is to 1. Sorry, 4 is to 4, 1 is to 4. So this is our frequency spectrum. You can see. So this is our main. See, this is 200 means FC is 100, right? If it is 200, then FC is 100. Okay. FC plus FM 100 plus 10. FC minus FM 100 minus 10. So this is the spectrum of AM signal. You can observe what is this, what should be this. If it is AC, then what should be these two sidebands? These two sidebands should be AC, sorry, EC. In our experiment it is EC divided by EC into modulation index divided by 2, means EC into modulation index divided by 2, correct or not? So it is less than half, that is good enough. So you can easily observe the spectrum also. Now let us see. Now I wish to go for closing this figure window because for other modulation index also we have to see the waveforms. So I will close these breakpoints also because we have understood how the code is running. Right now we will simply change the input and observe the waveforms for all the three modulation index, time domain waveform also and frequency domain waveform also. Now I'll be running the code, complete code at a time for different modulation index. Let us see. I'll take modulation index as 1. Let us observe for the same. My message signal I am taking 5 amplitude and the enter the message frequency once again I wish to take 10. Fine. And for the amplitude of carrier signal 5. Did anyone remember why I have taken message signal amplitude also 5 and carrier signal amplitude also 5? Because modulation index I would like to go for 1. So that's a reason. And coming to carrier frequency 100, because I already stated time limitation is there, so that's what we are taking 100. Let us observe what is the modulation index. Yes, modulation index is going to 1. You can observe in a command window. Modulation is index is going for 1. See here. And you can observe this very interesting waveforms you have got, which are very typical to understand in a regular theoretical explanations. See, this is your message signal, carrier signal. See, this is modulation index. M is equal to 1 means EM is equal to EC. You can observe these two signals are having same amplitude, but the message frequency is less, carrier frequency is high. So they are simply touching. They are simply touching at the 0. Okay, and you can observe here, if modulation index M is equal to 1, if modulation index M is equal to 1, then these sidebands will have half that of the major lobe. That major lobe, carrier frequency lobe is this much, right? Carrier frequency is of this much, right? So its half it will be, because what is the formula for sideband sideband amplitude? Sideband amplitude formula is EC into M divided by 2. Now right now M is equal to 1, as a part of which it will be EC by 2. If this is, just a second, if this is EC, you can observe around y-axis from 2 3 4 6, right? Here it is 1 2 1 8. Yes, it's around half, so it is fulfilling. Okay, so this is for modulation index 1. Now we will see what will happen for modulation index greater than 1. So for that, what you have to do, you have to run the code once again. Let us observe, but I'll take a different modulation index. For that I have to take message signal amplitude is more than carrier signal amplitude, right? So here carrier signal amplitude I wish to take carrier frequency I wish to take message amplitude I took 7, message frequency I will take 10, right? And then carrier amplitude once again 5 I'll keep once again 5. And coming to carrier signal frequency, signal frequency once again 100. See, I am not changing message and carrier frequencies, right? I am changing only message and carrier's amplitude. Keep that in mind, because I am changing only modulation index. Okay, if anyone wants to know like how the frequency changes, how the spectrum changes, so that can also be observed. So I'll do that in the next next type when I'll be running next time, and when I will be running, let us observe what will be the modulation index. It should be more than 1, because 7 divided by 5 goes to 1 point something, right? Let us observe, it is 1.4. okay, fine, that's correct. Modulation index goes to 1.4. So everyone, where you are observing modulation index, see, you are getting modulation index here. So now let us see how the waveform looks like. So waveform looks like this. You can observe here, yes, this is message signal, this is carrier signal, and this is modulated time domain signal. You can see here. Yes, in our theoretical concepts we used to go like this, right? Yes, means we are crossing 0 while plotting the signal, right? But you see here, sideband amplitude which is crossing half, more than half. Okay, because modulation index is more. See here, 1696 it is. Okay, and what about this one? It is 2346, means it's more than half, right? It's more than half. So that's the reason. uh, this is how the spectrum is changing for different modulation index, and also time domain signal is changing for different modulation index. Okay, so in the last set of simulation running the program, what I wish to go for, I wish to go for changing the frequency also. Okay, till now I kept the frequency constant. Now I wish to go for changing the frequency. let us observe this. Amplitude first iterations whatever I taken, like message amplitude 3 under modulation condition I am taking here, message amplitude 3, and message frequency I wish to go for 20. Okay, see what is the changes you should know theoretically. In the spectrum, whatever the sidebands are coming, no, they will go far away from the center frequency. Center frequency means which? Carrier frequency. Compared to carrier frequency, the sideband lobes are going far away, because previously it was 10 hertz. Previously the frequency was 10 hertz, but I kept 20 hertz. So FC plus FM. Okay, that concept. Let's amplitude I will keep 5. 3 divided by 5 implies modulation index goes to less than 1, means under modulation concept. Now carrier frequency I'll keep 100 as it is. Okay, see, observe here all of you. See here, my carrier frequency is 100, message frequency is 20. What does it implies? What is your upper sideband frequency? 120, and lower sideband frequency 100 minus 20, which goes to 80. So in that way we supposed to observe our frequency, then we can say the theoretical concept and the simulations are matching. Let us observe the modulation index 3 divided by 5 goes to 0.6. Let us observe, is it okay? Yes, 0.6 you are getting modulation index. Coming to the waveforms, see here. Yes, it is under modulated concept, right? Message signal modulation index is 0.6. Huh? This is message, this is carrier, and this is a under modulated signal. Fine enough, no issue. Coming to here, you can observe. Previously, this gap, this gap was of 10. Right now, this gap is of more 20. Okay, if it is 100, if it is 100 hertz, then this is of 120. Okay, is it is you can easily observe x axis, you can observe x is 100k here, right? Now observe here, what is x? Just a second. Yes, what is x? 121. Fine, means 100 plus 20 is 121, correct? You can observe, yes, means fc plus fm. Coming to here, what is x? 81. Yes, good, fine. Like 100, just a second, this is of 100, right? Carrier frequency is of 100, and lower side band will be of fc minus fm. 100 minus fm is how much? 20, so it's 80. Fine, so it is also fulfilling. So this is how am simulation can be done for modulated time domain signal and also modulated frequency domain signal. I hope you like this video. Okay, please hit like and comment. If anyone would like to ask any question or for any other queries, you please comment in the comment box. Thank you for watching this video. Thank you for your patience listening. Wish you we will have another communication related video in upcoming video. Thank you. Have a nice day.